Let us apply what we have learned about Fourier transforms in 3 dimensions to solve this very famous problem in elasticity, which is called the Kelvin problem. In the Kelvin problem, we have infinite 3D body with a point load applied at the origin where P is equal to Pi EI, let's say. So you have to find the displacement at any point x due to a point load applied at the origin in an infinite 3-dimensional body. And this is, again, as I said before, this looks like an unrealistic problem, but this is a problem that serves as the basis for solving more complicated and more realistic problems. Now, the first thing that we need to note here is that force PIEI, concentrated force PIEI applied at the origin, can actually be treated as body force distribution of this sort. So why? Because if you take the ith component of the body force, Bi is equal to Pi delta x, and then if you integrate both over some arbitrary volume, this becomes equal to 1, and therefore the integration over any arbitrary volume around the origin, so if you take a volume like this around the origin, the net force due to this this distributed load Pi delta x and load concentrated force Pi are the same. So the first thing that we need to note is this concentrated load applied at the origin can be treated as Bi equal to Pi delta x. So this is the trick that we use to to express concentrated load in as a distributed body force. Sometimes we'll also use it to represent a distributed surface traction, but in this case we are converting it into a distributed body force. So this delta x function allows us to do that. So now let us start with the Navier's equation of elasticity. This we have seen before, and in place of this body force here, we are going to replace it by this distribution, which actually represents a concentrated force at the origin. Now take the Fourier transform on both sides. So this one, if you take the Fourier transform of this, mu is of course a constant, and then you have two derivatives with respect to k. Each will lead to I zeta k. So I zeta k times I zeta k, and you will get ui bar, which is the Fourier transform of ui. And then lambda plus mu is a constant, and then you have a derivative with respect to k and a derivative with respect to I. So you will have I zeta I and I zeta k, and you will be left with u k bar, which is equal, and plus pi times delta x. Delta x has a Fourier transform of 1, so this will be equal to pi plus pi, and that will be equal to 0. So if you take this will be zeta k, and this will be minus zeta k, and this will be minus zeta I, zeta k. So take it to the other side, and you will end up with this expression. And from the tables of elastic constants, we can replace lambda plus mu by mu, and if you look at the table, lambda plus mu by mu is equal to 1 minus 2 nu. So we just replace it with Poisson's ratio, take the mu outside, then this is what we are left with. So this is the expression that we are left with, where we have simply replaced, we have taken the mu outside, lambda plus mu by mu has been replaced by 1 minus 2 nu, and then we have taken the delta uk outside. So this is a matrix, which we are going to call as A ik, and that is a function of zeta. So it depends on zeta, it's a function of zeta, and we can now express, so this aik is a function of zeta, this is actually a function of zeta, and this is how we can express it. So this will mean that if I say multiply by a m I inverse aik uk bar equal to a mi inverse pi, here I will get delta mk uk bar is equal to a mi inverse pi. So this will lead to ui bar equal to a, so I'm replacing m by I and I by k, so I k p k. So this is what I will end up with, where aik inverse, the inverse of a, still has to be determined. Now there are various ways in which we can determine this inverse. One way that we can use is, let's declutter this place. One way we can use it is explicitly write the 3 cross 3 matrix. A is a 3 cross 3 matrix, so we can write it as a function of the zetas at different places, and then we can invert it just like we invert 3 cross 3 matrices. We can directly invert the 3 cross 3 matrices. It's going to be tedious, but it's not impossible. Okay, so we will do it in a more rigorous way, but you can also do it, as I'm saying, you can put I and k, you can write down the 3 cross 3 matrix and then invert it. That is possible. But whatever you do, we are going to express now this as zeta square. Remember, zeta square is zeta k. We had defined that earlier. And doing that, we take mu zeta square outside, and then this is what our aik looks like. This is what our aik will look like. And now you can, as I said, either take it as a 3 cross 3 matrix and find its inverse, but whatever you do, this is what the inverse is going to be. This is aik inverse. Now, how did I get here? I am going to postpone that derivation to a little bit later, but just take it for now that this is the correct form of aik inverse. Now, once you have this, now you have the Fourier transform of ui in terms of this aik inverse, which is a function of zeta, and the kth component of the force that you have applied. So now we go back to the table and try to see whether we have this function. One of the functions that we need to invert is 1 by zeta square, and the other function that we need to invert is zeta k by zeta 4 Okay, and then we know that if I can invert this function, the ith derivative of that function will give me I zeta I. So the ith derivative will give me this. So I will try to see if I can find this function, inverse of this function in the table, inverse of this function in the table, and then I am done. So if we go back to the table, the 3D table, 1 by zeta square, 1 by zeta square is in the table, and its um, inverse is 1 by 4 pi r. Zeta k by zeta 4 is also there in the table, and its inverse is xk by r. So go back here. This and this. So this is 1 by, the inverse of this is 1 by 4 pi r, whereas this is minus 1 by 8 pi I xk by r. So zeta k by zeta 4 is 1 by 8 pi I, and a minus, I think, xk by r. So this is it. So when you have zeta I, then that would mean I zeta I would have meant that derivative of this with respect to xi, but now I can write this as I by 8 pi xk by r, and since I have zeta I, then it will mean that I can write it like this. So the derivative with respect to I of this would be I zeta I of 8 pi I zeta k by zeta to the power 4 minus, I think. So that would be the derivative, and if you work it out with this 4 into 1 minus nu, you will find that you exactly get the term here. You exactly get the term here. This term. This entire term. So you have to work it out. But if you work it out, this is the displacement due to a point load applied in the kth direction, displacement in the direction I due to a point load applied in the kth direction in an infinite body. So I can of course write this ui as 1 by 4 pi mu delta ik by r minus 1 by So if you apply a load in the kth direction at the origin, the ith displacement that you will get at an arbitrary point x inside the body is given by this function. So this is an example of what is known as a Green's function. We will have a lot more to say about this in the coming slides, but right now take this as a solution to the problem that we have at hand. Okay. So we will do another problem in 2D after this, which is similar to the Kelvin problem, but this is a very important result, and this forms, as I said, the foundation for finding solutions to much more complicated problems with involving infinite bodies.